out here to talk about the Geologic and Groundwater Atlas of Isanti County. When you came in, there were a few different things on the table in person. There was an agenda as well as paper copies of both the Part A Geology and the Part B Groundwater Atlas for Isanti County that we'll kind of look at quite a bit today, hopefully. And then we just wanted to start out. We are going to be recording just the presentations today in case there were people who couldn't make it. And so if they reach out to us, we can provide the presentations. Because of that, we do have a Tennyson warning posted here just to let you know, especially those remotely, there is a chance if you type in the chat or come off mute and talk that you will be recorded on the audio. And so we just like to give you a heads up. The whole purpose is just to distribute this. We may distribute it in the future, and we need to let everybody know that that's our intent, so that you understand. The agenda this morning is, once we've gotten this kind of squared away, the first people who we are going to have present is actually going to be Tony and Angela are going to tell us about the Part A and kind of give us an overview of what was found when the Part A was published. And we give Tony and Angela a very warm welcome.
Okay. How far afield I'm gonna scroll. Okay. Hi, I'm Angela Radke. I'm a quaternary geologist at the Minnesota Geological Survey. So I map the glacial sediments throughout the state in various counties. I personally did not work on Isanti County, but I have been working in Hennepin and Ramsey County. So I've been kind of working relatively nearby. And I also actually lived here in Isanti County over by the Green Barn, if you're familiar with where that is. So I'm here today to give you kind of an overview of the Part A of the County Geologic Atlas. So we'll go run through a few things here to start. And then Tony Runkle here is the, yeah. Yeah, I'm trying to talk louder. I'm sorry. I don't have the loudest voice.
I could try to get one set up. I project. I project.
I have a apology. There are two microphones. Extra. Press the power button.
Is this better? Okay, thank you. This will help me not having to scream at you either. For me, that was screaming. Okay, we have Tony Runkle here too. He's the lead geologist at the MGS, so he kind of knows everything about all the things, and then also maps the Paleozoic and overall bedrock geology here in Isanti County. So the MGS is a non-regulatory research and service center at the University of Minnesota, and we provide systematic geoscience information to support the people of Minnesota. We work closely with the university, government, and industry and community partners. And geologic mapping is one of the largest contributions that we provide at the survey, and via the County Atlas program, the CGA program. And why is mapping geology important? Well, it's literally the foundation on which our world is built. In and out. There we go. The geology contains crucial resources that lie below the land surface, which include energy resources, building materials, things for shelter, waste disposal, and obviously clean water, which is what we're very concerned about. Minnesota has many natural resources, including minerals, aggregate water, and so on. And mapping geologic information is vital to predict, plan, and protect all of these resources. The County Geologic Atlas program began in 1982. And it's a comprehensive mapping that we do county by county, suitable for managing mineral and water resources. So Part A is the physical geologic mapping that we do at the MGS. And then Part B is the groundwater atlas produced by the DNR. These atlases define the aquifer properties and boundaries, as well as their connections to the land surface and the surface water resources. I like to think of what we do as we map the container. So we map the thing that hosts the water. So that's sort of the way that a lot of groundwater modelers refer to what we do at the MDS. These things that we produce, these maps are applicable to land use planning, wellhead protection, source water protection, remediation, and so on. And they're valued tools by counties, state and federal agencies, consultants, researchers, etc. And here on the left, you can see a map of our current progress for mapping the counties in the state. I think the one that's coming down the pike soon enough here, and when we get this laser pointer going, you can see this here.
Yep.
Yale Medicine is coming soon. That's what we have to look forward to for another atlas on the way. And so we're making our way through. You can see the ones that are closer to the Twin Cities are obviously the ones that we've been doing more readily because they are closer. Okay, so what's on each plate? We have 6 plates that we produce as for part A of this UGA. We have plate 1, which is the database plate, showing all of the different data points that we use to generate the maps that we make. We have plate 2, the bedrock geology. Plate 3, the surficial geology. 4 is the quaternary stratigraphy. 5, sand distribution model. 6 is the bedrock topography. And we'll go through each of those plates here as we keep going. And then everything that we produce is available online on our website in the form of GIS data that you can download and use in a GIS program. We also produce 3D geologic surfaces. And then every cross section that we draw through the county is available to you. There are 6 of them that are printed on the actual plate. A nice pretty format, but the actual lines are also available. And then we create story maps and web maps for users that can visualize the data without GIS software. So where can you find the Part A publication here? So there's a couple places you can click on our website which is cse.umn.edu/MGS. So if you click here on this middle bubble, it will bring you to this page here where it has all of everything that we produce in a big long list. And it's probably hard to see on the screen here, but there's one that says County Geologic Atlas. So if you click there, you can search for Isanti, or you can search in the toolbar here. Just search for Isanti and the maps will show up. You can also click on this drop down here. Again, very hard to see, but it says County Geologic Atlas. You click on that. And if you scroll down all the way down, they're in alphabetical order, all of the counties that we have maps for. And you can click here on the top and it will bring you to the next page, which is kind of the home page for where all of these plates are located. They're all listed here as PDFs you can download. And then all of the GIS data is also available in this area on the webpage. Okay, so there isn't too much to say about the database map, except for this is where you can find all of the different points that we used to generate the geologic atlas. So we have all of the well records where those locations are, any particular data points that we at the MGS have taken samples of in order to make our surficial map or the quaternary stratigraphy. It also includes an image of well records here. So you can look at this one particular well record and see how this well was constructed. You can see how deep the casing goes, where it's screened, and also the type of material that the well driller described as they drilled the well. And those descriptions are vital for us to make our maps. So we rely heavily on how well drillers have described sediment in the subsurface in order for us to actually make sense of things here in the county. Okay, and then I guess it's time for Tony to talk a little bit about the bedrock geology.
Try without it first. Is it on now? Okay. Can you all hear me fine? Or should I use the microphone? All right. How's that? Is it working?
Yeah.
All right, good enough. Well, thanks for the introduction, Angela. As Angela said, I'm the lead geologist, but before I took on a lot of those responsibilities, I was one of the primary bedrock mappers for southeastern Minnesota, and including all the way up to Isanti County. this was the last map I'd made, so that's why I was on the hook to come to this meeting. I think that was 2016, something like that. But I really I still enjoy or wish I could go back and enjoy mapping, even though I don't have the time anymore. So I am glad to be here to explain the bedrock. And it is quite important because, as you'll find out in this meeting, is that the bedrock supplies contains the aquifers that are most widely used in Isanti County, including here in Cambridge, which I'll get to here in a minute. So what I will cover here is plate 2, bedrock geology, and plate 6, bedrock topography and depth to bedrock. And then Angela will follow me and talk about the materials that are on top of the bedrock. Okay, and I'll kind of explain that here in a few slides. So what am I talking about? I'm not actually talking about what it says here, which is surficial glacial geology, which is the unconsolidated sediment beneath the soil. That's what Angela is going to talk about. And 2 common types of unconsolidated sediment are shown here: sand and gravel and clay-rich sediment. If you're familiar with the word till, that's the most common clay-rich sediment. So all of that's on top of the bedrock, right? That's why in Isanti County, you can't see any bedrock, as far as I'm aware, unless I missed an outcrop when I was mapping here. You can in other parts of southeastern Minnesota, but here the bedrock's fully covered by this unconsolidated sediment. So for my portion of the talk, I'm going to remove the cover. And as I did so, what you're seeing on that map is the bedrock geology below the unconsolidated sediments. I'll explain more about that map in a second. Below that map is what we call a geologic cross section. So it goes from A to A prime diagonally across the county. And that represents what we would see if we dug a trench 1,200 feet deep from the northwestern part of the county to the southeast part of the county. We tried to do that, but Isanti County wouldn't give us a permit. So we do it schematically, all right? So it's a schematic trench, northwest to southeast across the county. So here too, I'm going to remove all the unconsolidated sediment that's on top of the bedrock. So now you're looking at the essential information on the bedrock geology of Isanti County. You're looking at it in map view, and then below that, you're looking at it in cross-sectional view. Okay, if I can get the laser pointer going, I'll give you some examples. So if we're way up here, it might be a little hard to read, but it says Precambrian igneous and metamorphic rocks, for instance, granite. If you were to drill a well in this area through the unconsolidated sediment, the first thing you'd hit is this, what we call just generally hard rock, the kind of rocks you see up in northern Minnesota. If you move down here to Cambridge, and I can't quite see what the map unit is there, so I'll have to walk over here. It looks like you'd hit this yellowish color, and that represents something called the Tunnel City group. Okay, so you'd hit a different material if you drilled through the unconsolidated sediment here in Cambridge, and so on and so forth. And looking at it in profile here, it's the same thing. Here you would hit granite or something like it. Here you would hit this little layer here called the Tunnel City group. That would be the uppermost bedrock. Any questions on that? Okay, and these rocks all have names. Some of you might be familiar with some of them. The one you might be most familiar with is called the Mount Simon Sandstone. And the reason you might be familiar with that, that's right here. The reason you might be familiar with that is that's the major aquifer for the city of Cambridge. There's a number of wells drawing from the Mount Simon Sandstone. Okay, do people have kind of a good handle on that so far? Just stop me if you have a question. And so what do these rocks look like? Well, when there's, if we have a break or at any time you feel comfortable, you can come here and see some examples. So this is a rock core from the subsurface, and it's actually this one right here. Not the same piece, but that's Fond du Lac Formation. And here's your Mount Simon aquifer. right here. Okay, a sample of your aquifer. You can come up and look at these anytime. So they've all got these names, representative rock types, granite, sandstone and shale, sandstone. Importantly, there are some finer grain layers with shale in them. And those are actually the layers that protect underlying aquifers, because water does not transmit through these siltstones and shales very easily. Okay, so there you can't draw a lot of water from those units, but they protect the underlying aquifer. So that's the bedrock geology. And now I said I'd be moving on to bedrock topography and depth to bedrock. And I think these are a little easier to understand. So again, we're moving, if we removed all the unconsolidated cover, the bedrock topography shows the landscape or the topography of the bedrock. Just like, you know, you've seen topographic maps of the Earth's surface or this region today, right? Here, this is a topographic map using colors that shows the surface that corresponds to this red line right here. Okay, and for instance, the dark green means lower elevation. And so what I'm following with my finger here is a buried valley that used to drain water a long time ago, heading northeast through Isanti County, but you don't see it today because it's buried by unconsolidated sediment. This map is somewhat similar. Instead, it's called depth to bedrock. So let's go back to this buried valley. This buried valley is at an elevation of 650 feet, okay? This is the same valley, but instead of giving elevation, it's giving depth to bedrock. I know it's a little hard to read, of greater than 400 feet. So you would have to drill more than 400 feet through unconsolidated material before you hit bedrock there. Another way to phrase it is that this is a map of the thickness of the unconsolidated material. So here it'd be less than 50 feet thick. Here it'd be less than 50 feet thick. Here it'd be over 400 feet thick. Y'all following me? Okay. Seeing a lot of nods. Just two more slides here, I believe. I already explained bedrock topography, but what I wanted to add was something that Angela referred to, and that is, you know, a lot of you have paper maps in front of you, but as you'd expect, everything we map is now available electronically as well, including as what we call rasters. So they're kind of continuous electronic surfaces or grids that will give you all the same information that you have in your paper maps. So here it makes it even easier to see. Here's the buried bedrock valley I talked about, going right through there. And then on top of that, we can add the geology. So now you're looking at both the topography and the geology. So if you drilled right here, it'd be really deep to bedrock. If you drilled right here, it'd be shallower to bedrock. And the first layer you would intercept is the Untitled sandstone. Right? That's the way the maps work. And virtually, I may even have a note of this. Yeah, all the geologic features, not just the bedrock, are available as grids. And that's important because, for instance, groundwater modelers need these electronic surfaces to create their groundwater models, to run a groundwater model. And last, just kind of as what I'm calling a look ahead to the CGA Part B, which you're going to hear about very shortly here. Those are images you've already seen, map and cross section. Here I've changed the color to show what becomes an aquifer in blue versus an aquitard in brown. And I mentioned there's some shaly layers that protect underlying aquifers. That's what the brown represents. And here's the city of Cambridge, a schematic well for the city of Cambridge, which I think that I don't keep up on how many wells you all have here in Cambridge, but I believe there's over 6. How many? Maybe some have been abandoned.
I want to say 10 or 12.
Yeah, and at least over the last 20 years, I believe they've all been fashioned in this more or less like this, some a little bit deeper, but they're drawing from the Mount Simon aquifer. And I'll just finish with information that maybe I'll get corrected on from the DNR people. But at the time I looked this up, which was a few years ago, the bedrock is the source of water for about 25% of wells in Isanti County. But most municipal wells, meaning high capacity wells, are in units like in the bedrock in units like the Mount Simon. That's it for mine. So now Angela's going to talk about what.
You got a question?
Oh, yeah.
There's some wells right in the city of Cambridge that were 19 feet. So where does that, what layer is that?
19 feet?
Yeah.
Well, yeah, Angela can tell you that. Yeah, that's perfect. Perfect segue.
Oh, another.
Angela might be able to answer that too. It always depends on what's filling the valley. So often it's quite, there can be at least some layers that are very sandy and gravelly. And especially if they have a clay on top that kind of protects the water quality, that can make it a good aquifer. If they're filled mostly with glacial till, which is clay rich, then you might have to go to bedrock. And I don't know if we know what's in the valley, do we?
Yeah, so as far as that bedrock valley, I have a slide, it's at the very end, but it will kind of illustrate what we really don't know about what is filling that valley, unfortunately. As you can imagine, drilling a well is expensive. And so the deeper you go, they probably don't want to have to go 400 feet to encounter the entire glacial section. So they'll probably stop wherever they find the best aquifer at the shallowest depth. So I'm assuming we have some constraint, maybe down to just a certain depth where they find that sand. And then as we keep mapping in those valleys, we unfortunately map it as undifferentiated. So we just have no information in order to differentiate what is in that valley. I will say the orientation of that bedrock valley fits the exact orientation of an ice sheet that came out of Lake Superior called the Superior Low. And so it's possible that that valley is filled with a decent amount of sand and gravel because the glacier would have utilized that existing bedrock valley to funnel meltwater through and then deposit sand and gravel within it. So it's possible, but I don't want to say that for sure because we just don't know. So, long story for a quick. And then as far as the shallow 19-foot well, there are a lot of sandpoint wells in this county. And the reason for that is there's a 20 to 40 foot layer of fine to medium grained sand at the surface that we attribute to the Anoka sand plain, deposited by Glacial Lake Anoka. So like where I live, I know there were a number of these sandpoint wells that are just used for like minor, just local personal supply for like a shop sink or something like that. So I'm assuming that's where they're pulling the water from is the Anoka sand plain, which is here in Cambridge. But if you go just to the east towards like Spokane and those lakes over there, you start to get into the actual glacial till. So you can't really just put a sandpoint well in and expect to get water there because there's no sand. Okay, any other questions before we talk more about glacial? Okay, so as Tony mentioned, I already talked to you about the database plate, and he went over the plate 2 bedrock geology and the plate 6 with the topography and depth of bedrock. And so now I'm going to try to go through these next 3 plates here that relate to glacial sediments. So the surficial geology, quaternary stratigraphy, so that glacial package of sediment from the surface down to the top of bedrock, and then we have the sand distribution model. So just a quick overview of geologic time. So the image on the left is a nice column schematic showing the differentiation of how we label geologic time with different names. The Precambrian, the very far right column there, encompasses 4 billion years of geologic time. So these columns are not to scale. A lot of the rocks that Tony went over are from the Paleozoic period, which is the green column there. And then now, as far as what we're talking about when it relates to glacial geology, we're talking about this tiny little sliver that's the same width as the arrow there, called the Quaternary, covering the last roughly 2.5 million years of geologic time. And then the image on the right is a nice depiction kind of explaining what each of these plates are representing. So plate 3, the surficial geology, is just kind of a snapshot of the material right at the land surface. Plates 4 and 5, the quad strat and the sand model, are describing the glacial sediment from the surface down to the top of the bedrock. So the thickness there, which as Tony mentioned, can vary from 50 to 400 feet thick. Plate 2, bedrock geology, is that very bottom layer. So Tony already talked about that. And then plate 6 takes into account everything, the surface topography down to the bedrock topography, giving you that depth of bedrock thickness. Glacial geology 101. So Tony mentioned glacial till, those clay-rich sediments. Glacial till is an unsorted mix of clay, sand, silt, and boulders deposited directly beneath a glacier. So if you have glacial till somewhere, you know that there was a glacier there, right? The glacier was right on top of that spot where you're seeing glacial till. And these are just some images showing you what that looks like beneath modern analogs. So we think of till as being clay rich, but it's generally a mix. We think of it more as like a loam, so kind of equal parts sand, silt, and clay. But the important part of it is that groundwater does not move as easily through it as it would clean sand and gravel. And when we display till on a map, we usually use green colors. Outwash sand and gravel, something that's deposited at the front of a glacier by meltwater. You can see kind of a braided stream emanating from this ice sheet here on the left image. So that's where we get those more sorted grains of coarse sand and gravel. And then we also get lake sediment that forms out in front of a retreating glacier in the form of fine-grained sand, silt, and clay. It can really range in texture, and I want to emphasize the fine sandy type of glacial lake sediment because that is very important for Isanti County. But we also have areas in the northern part of the county, like in the Brand area, where we have fine silty clay material. So we have kind of a varying amount of texture in our lake setting here in the county. So we use a ternary diagram on each corner or on each point of the triangle is 100% either sand, silt, or clay. And for glacial till, especially in Isanti County, we have generally ranging from a sandy loam to a loam texture. So roughly like 40 to 60% sand. And then, I guess like 20 to 30% silt, and then the rest being clay. So the textures that we get for till kind of are in that range with the green circle there. Outwash sand and gravel, as you might expect, is mostly sand and gravel. So it goes to the far sand corner on the ternary diagram. And when we map outwash on a map, we usually use warmer colors like oranges and reds, kind of trying to indicate that water moves more quickly through those materials. So it gives you that hotter color. And then lake sediment can range all across the clay to silt spectrum, but really you could draw this entire blue circle around the whole diagram because, as I said, lake sediment can just be a fine sand, which would then put it in the sandy corner of the ternary diagram there. During the last glaciation in Minnesota, we had ice that accumulated in Canada called the Laurentide ice sheet, and from there we had a number of ice streams that emanated from it into Minnesota. Two of them that are relevant to Isanti County are the Superior Lobe, which is an ice sheet that advanced out of the Lake Superior Basin, what's now the Lake Superior Basin, from the northeast, all the way down to the Twin Cities and south into like Dakota County, for example. And then we had the Des Moines Lobe, which entered Minnesota from the northwest. And there was a little offshoot, little thumb of it, that's called the Grantsburg sublobe that kind of protruded and advanced over top of the area that the Superior Lobe had previously advanced into. So you have two different ice sheets entering Isanti County during the last glaciation, roughly starting 75,000 years ago until about 14,000 years ago. So just to show you again, ice came out of the northeast, Superior Lobe, and then we had ice coming out of the southwest, the Grantsburg sublobe, into Isanti County. And the reason this is important is because each of these ice lobes carried a unique rock assemblage. Rocks are within the sediments. So if any of you have been along the North Shore, you've probably seen the rocks that are along the North Shore there. Lots of igneous basalts, some red-colored rhyolites, hard rock, lots of iron in those rocks. So Superior Lobe sediments generally are reddish in color because of that high iron content and lots of igneous rock in that material. And then rocks from the Grantsburg sublobe generally have a lot of carbonate and a lot of shale coming out of the Dakotas of Pierre Shale. So these two different glaciers carry very different types of materials, and that's how we are able to distinguish between those different layers in the subsurface because of their unique characteristics. So plate 3, just to emphasize a few things from the start here. There's a big blue area kind of covering most of central Isanti County. There's some areas that are in greenish here, and then we have some more blue on the northern side of the county, and I'll kind of explain more of that as we get going here. To collect data for making a map, we go about that in many different ways. You can see on the left, we have somebody using a hand auger to just take a sample of the material in the first, roughly 4 or 5 feet. In the center there, there's a photo of the person who actually was a co-author on the surficial map, Gary Meyer. He's climbing a outcrop there along the river. So we'll utilize any natural cuts in the landscape in order to take samples and get a sense of the material. And then on the right there is our Getting Soil probe. So it's a little drill rig mounted on the back of a pickup truck, and there's a auger attached to it. It's only a 2-inch diameter auger. We drill down to a maximum depth of 15 feet, and we pull up material every 4 feet, take sample of it, and then we will be able to get a sense of the geology right at the surface. Here are some photos from the actual fieldwork that occurred in Isanti County in the 2014-2015 season, so it's been a little while now. But again, a photo of Gary Meyer there on the left, pointing to a nice outcrop of glacial till. Sorry, sometimes this mic goes in and out. So he's pointing to some glacial till. That is actually what we call the Twin Cities Formation. It's a till that was deposited by that Grantsburg sublobe. In the middle there in the bottom, there's a nice picture of a bunch of different types of sediments, and we'll go through a little bit what each of those different layers are. And this is again an outcrop from a canoe trip actually that took place along the Rum River just north of Cambridge. So Gary and another person went out and explored a little bit. We also will utilize any random cuts that are in the landscape from maybe someone's digging posts and stuff like that. So the picture with the GPS, the yellow GPS device, is a cut through the glacial Lake Anoka fine sandy material at the surface there. And then on the right, we have an image of the sediment on the actual 2-inch diameter auger from our Getting Soil probe. So that's what that material looks like when it comes up out of the ground. And then we'll take samples of it, bring it back to our lab, analyze it for texture, look at the rocks within it, and therefore make our glacial maps. So here on the left, the big image is a digital elevation model of the surface topography in Isanti County. So the warmer colors are the higher elevation areas, and the bluish colors are the lower elevation areas. And so the dotted line that you see kind of going in the northern central part of the county here, you can follow it all the way along this way. So this area is showing you the northern extent of what we call glacial Lake Anoka. There was a big lake that formed throughout the county as the Grantsburg sublobe retreated. And that's responsible for giving you all of this nice fine sandy sediment at the surface in much of the southern part of the county. And this is just showing you, this is not what it looks like, but what it theoretically kind of looked like when this lake was forming. There are also other features on the northern side of the county called the Pine City Moraine. This boundary marks the northernmost extent of the Grantsburg sublobe on its western flank. So what you might find here is some evidence of different kinds of landforms that indicate that the ice sat there and stagnated for maybe 1,000 years or more as it sat and melted in that position. And so we use the topography and we use all of the natural cuts in the landscape to help us make a nice geologic map. So you kind of go back and forth here. You can see in those low spots in the blue is where glacial Lake Anoka is mapped. And then areas in green are where there's glacial till at the surface because it was sitting at a higher elevation in the landscape, so it was not underwater when the glacial lake was forming. So I kind of just wanted to throw that in there. And then glacial geologists like to tell a story. So we put together a nice schematic of the glacial history of what we think happened here in Isanti County. This is on the surficial plate. So if you'd like to read through a little bit more closely, you can kind of see there was a nice sheet called the Grantsburg sublobe that advanced. and it retreated, and as it retreated, there was a big glacial lake that formed. And then this is just showing different elevations of the glacial lake through time. So, okay, so that's the surficial plate. We have plate 4, the quaternary stratigraphy. So we're looking at all the different layers of glacial sediments throughout the last 2.5 million years. So this would include glacial sediment from before the last glaciation. So these are potentially hundreds of thousands of years old. The way we make these maps is by contracting with a drilling company to drill a rotary sonic drill hole. It drills core in a 4-inch diameter, and it's extruded into a plastic bag here and put on these tables. And there's a couple of field techs there chopping it up for us and putting it in boxes so we can bring it back to the survey and open up the core, get a sense of what that material actually looks like. This run, for example, is all glacial till on the table here. So this is what we do when we break it open, take pictures of it, look at its color, its rock type, and therefore we can use these cores to say like from 0 to 50 is sand, from 50 to 100 is till, and then so on. So that's how we build these different layers of glacial sediment for making our plot strat maps. Here are a couple photos from the core from Isanti County. On the left, we have a picture of the sediment deposited by the Superior Lobe, so that ice that came out of Lake Superior during the last glaciation. It's pretty rocky and sandy, so it comes out as a sandy loam texture. And then the photo on the right is a picture of what we call the Meyer Lake member of the Lake Henry Formation. It's a long name, but basically it's a grayish colored till that came into Minnesota straight from the north, and it has a moderate amount of carbonate, a lot of crystalline rock, and not too many pieces of shale. So again, when we see layers in the land surface from our surficial mapping, this is what we're trying to depict in our quaternary stratigraphy. So you can see those obvious color differences between the till deposited by the Gransburg sublobe in yellow and the Superior Lobe in red. And then this picture of this outcrop here on the right was from that canoe trip along the Rum River. And there's actually 4 different layers of glacial sediment just in this one photo. We have the upper till, which is the Gransburg sublobe till. We have something called Glacial Lake Gransburg that formed as the Gransburg sublobe was advancing. So there's a layer of lake sediment there, silt and clay. Then we have red Superior Lobe till, which is evidence of the Superior Lobe being in this location. And then there's even a layer of sand below that. So there's a lot going on in glacial settings, and we're doing our best to depict all of these different types of materials and all the different layers in the subsurface with the plot strat plate. And the way we do that is by drawing these things here. Each of the lines going straight up and down are well records. And so we're looking at the well records very closely, and where they describe sand and clay is where we're drawing our different boundaries for our different glacial layers. So here's an example of 2 core logs from 2 cores that were drilled in Isanti County. One is here in the center of the county, close to Cambridge, and then here in the southwest, closer to Elk River. And basically, what we do is we describe all of that material that we find in a core. So any of these blue colors are lake sediment, greens are tills, this peachy color is sand. And so we're telling you from here to here is sand, from this depth to this depth is sand. And knowing what we see in a core, we can then draw the cross section to exemplify what we see in the core. So if I just put all these arrows up here, you can see each of these different layers that we found in the core correspond to these different layers that we're mapping here in cross section. That makes sense. Okay, so then after we draw all these cross sections and we literally say, here's where the sand is, we can use the software on the computer in GIS to depict where the sand is instead of just in cross section view, but from like a bird's eye view from the surface. And that can just be an easier way to see where there's sand throughout the county. So again, in cross section here, we were able to draw the thickness and extent of Glacial Lake Anoka. And so everything in this brown area with the little squiggly contours in it, that's the extent of Glacial Lake Anoka, that surficial sand plain. And we modeled it generally roughly 20 to 40 feet thick, and obviously it varies in thickness throughout the county. There were a number of sand bodies deposited by the ice that came out of Lake Superior. So these are just a few of those. We think that the Superior Lobe advanced in 3 different phases the Atumba, St. Croix, and Emerald phases. And each of these images are just showing you the extent of those sands. They're going deeper down into the subsurface as you go to the right in this figure. So there was a lot of sand that the Superior Lobe generated. And then this is the image I was mentioning about the Bedrock Valley that kind of cuts southwest to northeast through Isanti County. So the image on the left is showing you the material that we have called undifferentiated. So the glacial sediment depth and thickness of that we just do not have information about. So you can see much of that material lies within that Bedrock Valley. We have better constraint in areas where there's people that draw groundwater, where the wells are drilled. So areas that are more rural tend to have less information, and that makes it more difficult for us to make a map. So that's just trying to show you that. And then on the right, we have the number of sand bodies that we've encountered in Isanti County. And so this is just based on our mapping, if a well record hits however many different layers of sand within one well. And very generally speaking, in the western portion of the county, it seems like you might have a higher chance of finding sand and gravel in the quaternary sediment in the county. And then I just wanted to end with a nice canoe trip along the Rum River. And if you have any questions.
All that work done, where's your funding come from?
Maybe Tony can speak more to that.
Sure. For the Atlas program right now, it's a combination. Most comes from the Environmental and Natural Resources Trust Fund, which is managed by LCCMR, the Legislative Citizens Committee on Solar Resources. And we have to go back to them every year or two and ask for money to continue mapping in other counties. There's also money available through the clean water funding, which is, I believe, the 1/8 of a cent sales tax that was voted in water money. Yeah. So, and then we do have a base budget that doesn't cover everything, but new computers, everything, keep the lights on, that kind of thing. That's our base funding straight from the legislature for the most part.
No, the Natural Resources Trust Fund that Tony mentioned, that's the lottery dollars that are earmarked for natural resources projects in Minnesota. I was gonna mention it at the beginning of mine as well, because we would not exist at the DNR either. We have essentially a very similar funding makeup for our products that we do for the Part B. And so that's a very good question. Thank you very much for bringing it up.
Said lottery, right?
Yeah, those are.
Anybody like to play both ends?
I have another question. A friend of mine went up Lake Superior, got a bunch of rocks from sauna. We said keep the sauna up and they exploded.
Oh.
So what could cause that? In a sauna, I mean, he was down there when it exploded. Was there some kind of in the rock itself? But he got it from Lake Superior. I was there when he picked it up. Shore, Lake Superior.
So rocks along Lake Superior that exploded in a sauna?
Yeah.
Oh, that's interesting. I truly do not know what to think about that. Do you have any thoughts, Ruby?
A guess off the top of my head is they had small fractures in them that could hold a little bit of water. When you heat them up,
Pressure.
yeah, the water expands and fractures the rock.
Sounds
Curious
dramatic.
because I saw in sauna after they,
Oh,
I mean, luckily he wasn't in there.
Oh, wow.
wow. Okay. My
Yeah.
goodness. Yes.
Yeah, just out of curiosity, how many wells?
That I don't have it off the top of my head.
How many wells did we
I
use?
should have read that.
Yeah, I don't know unless it was in your
it's-
database plate.
Yeah,
Was it on that slide?
I'd be happy to look that up for you and get that. to you. Yes. It's like to finish.
50 is one.
Right, it's probably at least 2,000 or.
Yeah, I
more.
would say a handful of
Yeah.
few thousand.
Like I'm thinking of like Hennepin County where it was like 40,000, for example, and that's a much more, populated county versus Isanti. I think I saw maybe 5 at the most.
5,000.
Yeah, that might even be more. I'll have to look to be 100% sure.
That's good enough.
Okay, okay.
In the thousands.
It is in the
Definitely in the
thousands, yeah.
thousands.
Like, for example, but there are even more wells than that. Like where I live, my well, there's no record for my well because it was drilled before we were taking good records of it. So I'd love to know what I'm pulling water out of at my house, but
I got Cambridge City municipal wells on your map, and those are really neat, I suppose.
yes. So I don't know if I have the exact cross section that this is the C to C prime cross section. So actually, I think this one does go through roughly where Cambridge is. You know, it would be, I don't think it actually crossed exactly where it would be, but yeah, these well sticks that are in the cross sections, if they went down into the bedrock, you would see it going beyond where the pillars are from the glacial sediment. So
When I looked them up the other day, but I can't remember numbers well, I think I remember 600 to 700 feet for some of the Cambridge wells. So,
Have to look.
okay.
There's also something called county well index, which you can specifically for
Yeah.
all the stuff.
Mhm.
I plan later when we do exercises to actually introduce the county well index and pull up the website. It's an online database where you can like enter in your address and see what wells are around you and if your well is on there and find out information. So we'll talk a little bit more about that a little bit later too.
In regards to the wells, there's probably a dozen drillers in Isanti County. Like, do you see a big difference in the reports you get from one well driller to the next?
absolutely, yeah, and in fact, it can vary just, you know, in time and because of different well drillers. I think, you know, the well drilling, their goal is to find sand, right? So it seems like the sands are described a little bit better than like the glacial tills are. So they're, you know, doing what their intended purpose is to find water. So there's that. And then, yeah, like, you know, it just depends. Like, I think things have become a little bit more standardized in the last, you know, 40 years or more now with the whole MDH and CWI database and everything. So hopefully newer wells are typically have a little bit more, you know, detail, but, you know, at the bare bones, I would say, is just for a well description to just say clay, sand, clay, sand, clay, sand. Now, if they give you more color or clayey sand, but that can be helpful too. But yeah, I think definitely as you're making a map, you can kind of see like, oh, okay, this was drilled by this well company. And so I kind of know what to expect for like how they typically like to describe materials versus another company.
So I have two parts. What, do you do this by county by county?
Yes. Yep.
And how many counties are left for you to do?
I think there's only like, I think it's less than 10
Yeah, that are not,
that are not.
there are
signed.
many that are not finished. There's about 8 or 7 now that have not, the county board has not signed on to have one done. But the others are either finished or in progress. And that's the part A, and part B has to wait for us before they can get started. So,
I have rough numbers. I think the part A's, I think you guys have approximately 6 done. It's
Right.
like in the 50s, I think, that are done. And then the rest are either in progress or the 8 that are not started. And
okay.
Right. Yeah, there's 8 on the map. And this also doesn't include some that are being like redone. Like, for example, I'm working on Ramsey County right now, and there is an atlas for Ramsey County, but now we're going to make a new one with more actual like digital GIS data in line with our new recent atlases in that area. Scott County is getting cross sections as well. But right, there's 8. You said 8 that are not currently signed, that are in white on this map. The red counties are completed with a CGA atlas, and then in yellow are all of the counties that we're currently working on. Like as far as well data, I think we have over 500,000 well records in our county well index database. So we have, you know, 500,000 well records. And I believe as compared to other states, especially in the Midwest, I think our database is like incomparable. So I think we're very lucky.
Yeah, the engineering firms, geoengineering firms, like the big ones like Bar Engineering, O'Brien, Intertech, that work in a lot of different states in this region, they say in our neighboring states, they don't have anything close to the kind of well data we have, nor the mapping. I know Minnesotans aren't supposed to brag, but we're doing better
I think
than
we can.
neighboring states.
So this, already this morning, we had great discussion of the geology across Isanti County by Angela and Tony. I want to thank you guys. That was absolutely fantastic. I also want to really thank Samra. She helped coordinate today's event quite a bit and significantly, and we would not have as successful of a turnout today, I don't think, without her assistance in scheduling and setting up our event today. I also want to just acknowledge, so again, I said earlier, my name is Vanessa Barata Person. I'm the supervisor of the Groundwater Atlas group. I'm here talking to you today about Isanti County because I am one of the authors on this report, but I just want to let you know, it was really a team effort to get this report done in our group. The first original author, we had two primary authors to start with, and one left for a good job opportunity, and one retired during COVID right before they finished up. And so I consolidated the end of the report as well as much help and assistance from my team. There's a total of 8 of us now, but we've been definitely adding staff recently due to a lot of retirements. And so this would not have been possible without everybody on my team and their assistance. And I will do my best to represent our Part B, but I did not do the primary initial work either, just like Angela said. And so I just want to let you know, I can definitely get you answers after if I cannot answer right away during the presentation today. And again, I just want to acknowledge our funding sources. We would not be here without the Environmental Natural Resources Trust Fund or the Clean Water Council. They have been very big supporters of our work. Like Angela said, these programs started in the 80s, and there was a big push in the kind of late 2010-ish era, 2009, to really start increasing how quickly these reports are coming out because they're starting to see the value of them. And so we've been definitely gearing up since then and trying to get more reports out. So just to kind of give you guys an outline for today, I'm going to start out as well of showing where you might locate our Groundwater Atlas product online. Many of you here in the room should have paper copies in front of you, but if you get home and you'd like to look at a PDF version or zoom into a digital file or access our GIS files, I'm going to show you where to locate those. I'm going to just do a little bit of groundwater basics. Some of it is not really needed because I feel like Angela and Tony covered quite a bit during their presentation, but if anybody has any questions, we'll talk about that. And then the remaining 5 items here on the outline is actually the core sections of our report. And so we'll kind of hit on those as we continue throughout the presentation. So first off, where do you find our Groundwater Atlas product? From the MGS, we have our own website online. You can kind of access it in 2 different ways. You can either type in mndnr.gov/groundwater mapping into your favorite search engine or your favorite browser, and that will get you to our main page, which is on the top right figure there. You could also just go to any search engine, Google, Apple, anything, and you can just type in MNDNR Groundwater Atlas. The first thing that pops up should be our MNDNR website. And this Groundwater Atlas program, if you click on it, it will also get you to our main page. Once you are on our main page, there is right under our main photos is a groundwater atlas. Again, it's hard to see on this, but it's also this link if you had searched, and that will get you to our main County Atlas series page. So once you get to the County Atlas series page, there's going to be a short section on the top, just giving a broad overview of what is in that Part A, geology, because we are a 2-part report. The Part A is the geology that Tony and Angela spoke about. And then the Part B is our groundwater and hydrology, which we're starting to talk about now. Beneath that kind of description, there's going to be a list of letters and an atlas is by county. You could scroll down and it's a long list of all of the counties, but to make it kind of quicker, if you click on any of the letters, in this case, I for Isanti, it will pull up the actual area and section for the I's. You'll see that we have a Part A geology, and then there's a blue date after it. That is a hyperlink. So if you clicked on that blue date, that is going to bring you to the MGS's website, to that final page that has all of their plates. And then below that is the Part B groundwater hydrogeology, and it has the PDF versions of the report that we put out. We also do 2 plates or bigger scale maps in our report as well. And then it also has a link to access GIS files if you're using Geographic Information System to digitally look at our products. And so what's in our report, just kind of a broad overview. Within the report itself is all of the findings, all of the summaries, all of the descriptions. On the Part A plates, they have all of their figures and their descriptions on their plates on the big maps. Our plates are just the graphic, and the actual descriptions go along with the report. And so our report has kind of 4 really key sections. There's some other subheadings, but they are hydrogeology and groundwater flow, water chemistry, groundwater pollution sensitivity, and groundwater use. And then our 2 big plates is, the first one is our water chemistry plate. It's very similar to the database plate that was described by the Part A. It is essentially a big scale map of all the water chemistry data that we used to develop our report. And it's symbolized by all the different types of aquifers and highlights the chemistry all together in one big plate. And then we have hydrogeologic cross sections, and that's similar to how Tony, when he was presenting, he kind of made it tan and blue a little bit on those geologic layers to show where were aquifers and where were those protective layers, those finer grained shales that Tony talked about. We do essentially that for all of the different glacial layers and bedrock layers to show the groundwater. And then we also have just those, electronic files of those PDF versions on our website, and then also the GIS files. So we discussed kind of where the Part A's are, how many are done, what's still left to do. This is the status map for the Part B's. You'll notice we have a lot of more areas that are in the kind of whitish gray color that is not started. As Tony mentioned, we can't start our work until they are done with their work. So if you kind of squint back and think back a little bit to their status map, anywhere that they had read a completed product, we pretty much have already started in some way. So anything that is a dark blue on this map, 37 counties, we are done with for our groundwater report. And anything that has kind of a striped light blue hatching on it, that is where we are currently in progress. We just published Isanti this summer, and as an upcoming kind of teaser, Houston County should be coming out in the next couple of months, as well as quite a few other counties will be moving forward. So I like to just kind of point out, how can these groundwater atlases be used? There's kind of a number of different things they can be applied for. It could be if you're planning a location for a well, say even for a private supply, or as Tony talked about, municipal supplies or big users like the city of Cambridge. If they need to put in a new well, they can kind of look through our products and see what water resources are available in an area. For protection of groundwater resources and managing groundwater resources. Just education, what water resources are available in a county, what are people using? These are things that you can get by looking at our products. Pollution sensitivity of aquifers, that is the biggest kind of priority within our group and our reports. Community development planning, infrastructure planning. And again, those GIS layers that we have available, those are things that sometimes even counties, if they have their own GIS databases, they will integrate our GIS data so that it's more broadly available. So our group at the DNR, we manage a few other products that we like to just kind of let people know about in case they don't know about them. We have what's a spring shed, and karst database. So we have a database developed in the last 10 years of where all of the springs across the state are located. It's definitely not comprehensive, and it is something that if you yourself have a property and have a spring on it and it may not be located there, please let us know. We're always trying to add additional information into that. There's a karst features inventory as well. This is identifying, where are caves, where are different types of sinkholes, things like that. And then we also have what's called a groundwater tracing database. This is largely in southeast Minnesota, but what it is we actually put dye in the ground and monitor where water moves to see, especially in karst areas, how waters move. We have what are called hydrogeology atlases. About 10 years ago, there was some interest in having some of our products available on a broader scale than just a county-wide scale. So a few of our products, we did scale up to a statewide version with slightly less resolution. So our near surface pollution sensitivity, as well as our water table elevation and depth to water table maps are available on our website on a bigger scale. We have a map that's called the Groundwater Provinces map. It just kind of summarizes all of the different kind of regions. It breaks Minnesota up into regions based on kind of their geology and how that the implications of that to the water resources, and kind of summarizes what the water resources are in different areas. And then also we have what are called regional hydrogeologic assessments, and those are largely in the western portion of the state. And before we had individual county atlases, we did some studies that were a little less detailed on bigger, like 4 to 9 county scales, just to get some information. That was largely in the late 90s, early 2000s, before we really started doing individual county products everywhere. So just a little bit of groundwater basics for terminology. Angela and Tony did a great job of kind of talking about, this is like if we had a big trench, hypothetically, and here's our land surface with nice little trees and a stream. On the left here, we have a well that, a hypothetical well that's pulling water out, and a stream where a lot of groundwater is pulling to that. Some of the things we just want to point out. So directly under the surface, we typically have what's called an unsaturated zone. It's sediments that there's not water filling all of the pore spaces. So water moves through it and ends up in a different place. At some point in all sediments, be them fine grained or, like till, like Angela said, or sand and gravel, at some point, all of the pores do get filled in between. And that kind of line here, this dashed line where we start to get everything filled with water, that's what you'll typically hear a water table. That's the point at which everything below it is saturated. And then the first kind of place where you might get water is from all of that water right underneath the surface. And it usually doesn't have a protective layer above it, or it may not. And in that case, it's called an unconfined aquifer, or in our report, we talk about it as the surficial sand aquifer. And so you'll hear us talk about that today. Below that, we have what are called confining beds, or the tills, or the fine-grained shales that we heard about earlier today. We also, you'll hear them called aquitards today. So water readily moves through that unconfined aquifer, or that surficial sand aquifer, but then it runs into a material that it doesn't move through as quickly. And so it's limiting flow. And so that's an aquitard. And below that, we have what are called confined aquifers or buried sand aquifers. And eventually we will get to bedrock aquifers, like Tony has already answered and brought up for us with the Mount Simon. Before we move, or one other thing to note, in this really shallow, unconfined surficial sand system, water falls as rain or snow or precipitation. It goes through the sand and it ends there, and it can happen pretty quickly. It can be days, it can be weeks, up to a year to get to, say, a stream or maybe where your well's pulling that water from. But as it runs into more and more of those kind of protective layers, that slows it down a lot. And so we can move to centuries or millennia or much longer time scales that it takes for water to get to those different depths. Does anybody have any questions about some of the terms I've used at all before we move on? Okay. So jumping into our report, the first thing you will run into in our report on pages 1 and 2 is just going to be an executive summary. This is a great place to start. And I encourage those in the room and even those remotely, if you pulled up the digital file, to kind of go along, look at the report, get to know it. Page 1 and 2 is an executive summary, and it overviews the results for the entire report. It goes through everything, every single one of our major sections, and it gives you a taste of what the results are. And it tells you where you might go, essentially, to look for a specific thing or that you may be interested in. But after that executive summary, our first major section is on hydrogeology and groundwater flow. So this section, what we're doing is we are linking together that container from the part A to what we're talking about when we talk about aquifers. We are showing that if you went to the part A and you saw this sand unit, how are we displaying it or calling it in the part B? So we're linking those together with the hydrogeology. And then groundwater flow, we're looking at where is water moving? How is it moving at this kind of in the shallow water table and in those deeper sands and gravels and bedrock units that were discussed this morning. And so this is pages 5 through 17 in the report. So as kind of a summary, like I said, we have surficial sand aquifers. A lot of them are in that big sand plain that Angela mentioned in the southern part of Isanti County. It's mostly coarse grained sand and gravel from the last major glacial advance, and it hosts approximately 7% of the wells in the county. And so, as you mentioned and asked about that 19-foot well, there's 7% of the county wells are actually in really shallow surficial sand units, directly kind of linked to the land surface. There's buried sand aquifers across the county in those glacial layers, those successive layers of till and sand throughout the county. And that's about 67% of the wells numerically, as Tony pointed out. So that's just looking at how many wells there are. But a lot of the big volume users are using those bedrock aquifers, like Tony pointed out earlier. And then we do have bedrock aquifers. There's 2 major kind of bedrock aquifers that are utilized across the county. And there are approximately 26%. And so Tony and I were only off by 1%, which is in our estimates, which is pretty good with that. So to start off, I like to this is one of the first major figures. There's a location map, which is figure 1 that I didn't show on the slides today, but this is figure 2, and it's a hydrostratigraphic column of all the quaternary or those unconsolidated sediments. So all of those sands and gravels that Angela told us about. And so there's one additional column in the actual report that says which of the advances and retreats it came from in the part A, but for visualization, we are comparing on this column what was presented in the part A to things that we're going to discuss in the part B. So the left side, we have all of those different sediment types, those textures that Angela told us about. And then we have the same color coordination and the names that are applied in the part A. And then we have a column for the part B units. In this case, all of the names match. There are some counties where we may group things together, and so this would show that. But in this case, we are same names for the different units. And in the part B column, so those sand and gravel units mapped in the part A are typically, are going to be what we call aquifers in the part B. And they are all on most of our figures or in our cross sections, they're shown with these patterns. So like the SS has all of the little dots on it. When you see our cross sections, you'll see that pattern to indicate all of these different aquifer units. Whereas our tills or our aquatards or protective layers are in these shades of gray. And you'll notice that there's different shades of gray. Some are lighter, some are darker. What this is showing is it's kind of the relative hydraulic conductivity or really an estimate of how readily water will move through it. So really light colors, it has greater than 60% sand. It's very sandy. Water will probably move through it more readily than, say, if we have something that has less than 30% sand. So the darker shades of gray, you could read as probably a little bit more of a protective layer than some of the stuff that is a lighter shade of gray. And then at the very bottom, the UPS unit, we show as kind of a brown, as Angela pointed out, like she showed like the big valley that we don't have a lot of information about. We don't know if it's sand, we don't know if it's gravel, we don't know if it's till. And so we're not going to try to guess at which one it is. And so we display it with a different color. Yeah, so quaternary is that time frame when Angela showed us that big column of like stratigraphic time figure and showed the little arrow indicating the quaternary. It is the last 2.5-ish million years. It's a glacial time reference. Yep. Okay.
There's a glossary too in the back.
Yes.
There's a lot of terms.
Yes. Yes. There's a big glossary in the back. So the next figure that we have in our report is a simplified surficial geology map. And so Angela showed us the very detailed map of the surficial geology. When we are talking about the groundwater, we're looking more at where is the sand and gravel, where the water resources are. And so in our map, anywhere where you're seeing like a yellow or an orange color is a place where there's sand and gravel at the surface, versus anywhere that it's white is a finer grain till at the surface. The colors and the shades of yellow and orange on this figure are showing how thick that surficial sand and gravel is. And then we also have just these little areas of dotted pattern on here. And what that is it's an area where that surficial sand is in direct contact with one of the buried sands or buried aquifers. So there can be all of these till units and sand units, they were deposited by glaciers and they don't exist everywhere at the same thickness. And so there are pockets where that finer grain material may have eroded away. And so these are areas where the surficial sand is right above what might be considered a buried unit in a lot of other places. And so these are areas where you can get much deeper pockets of sand or big stacks of sand, as well as these are also possible places where if some type of contaminant, let's say, were to get into this surficial sand, it's now also in contact with some of those buried units, is what you can kind of see that. We then, like I said, we talk about groundwater flow in this section. The first thing we talk about is that water table. As I said, this is the direct spot where saturated sediment exists across the county, and it exists everywhere in tills and in sands and gravels. So this is a water table elevation map, figure 5 in your report. You can see the warm colors, kind of reds and yellows and greens are the high points of this map. And the blues and progressively darker blues are the low points. There are kind of 3 major watersheds that exist across Isanti County. The Rum River watershed is by far the most prevalent. It covers really the majority of the county. And what our maps are showing with the arrows and the color changes, because water is moving from high elevation to low elevation, is that for most of the county, water is flowing towards the Rum River. But up in the northern part of the county, there's a few little spots where it's actually flowing towards the Snake River. And in the southeast kind of part of the county, there is a portion moving towards the lower St. Croix River. We also make a depth to water table map, just like they make a depth to bedrock map. What we do is we take that water table elevation from the last slide and we subtract it from the land surface elevation to get us how far beneath the surface you might encounter water at a given point across the county. And we found that the large majority of the county here is this kind of yellow, light yellow colors, which in our map is showing like 0 to 10, 0 to 20 feet. It's relatively shallow depth to bedrock. There are some areas where you definitely see some deeper colors here, up to 40 to 50 feet deep. And we have this stippled pattern overlaying here, which that's where that surficial sand aquifer is. When you have a really sandy unit towards the surface, water moves through it a lot quicker and is not held in the sand as readily. And so it's not surprising to see some stippling in really sandy areas.
So going back to that 67% of the wells, what depth are we talking about?
So the 67% is in the buried sand aquifers. So we're going to start talking about those in a little bit, but those can vary from, anywhere from the surface down to that bedrock surface that they were showing. In some parts of the county, you can have buried aquifers at 50 feet below the surface easily, but in other parts of the county, it may be 175, 200 feet, or that valley is up to 400 feet. So there's a variety of depths and different aquifer resources that it could be at. Yeah.
And to that point, the other 26% go through bedrock and then the next aquifer.
They pull from bedrock aquifers. Yep. And to point out, so we'll get to this a little bit later, but Tony has already shown this, those bedrock aquifers, they exist across much of the county. The Mount Simon kind of extends all across almost. And the Tunnel City Wanawak is kind of midpoint down to the corner. And down here, they had a depth to bedrock of about 50 feet. And so really, and it may be close to their only option because there's just limited resources above the bedrock in certain parts of the county. So we also make what are called potentiometric surfaces. This is what we do is we contour the water table elevations or the elevations of groundwater in wells. So we look at different well points in different aquifers and we can actually make a map of how groundwater is moving within those aquifers. Now in Isanti County, I just want to go back real quick. On this hydrostratigraphy figure, you'll notice there were 2 additional columns on the far right. There's a groundwater flow figure. What we're showing here is if you want it, so we grouped together some of the different quaternary units when we made a groundwater flow map. We made individual maps for every single one of the different aquifers, but in some cases, some aquifers have very limited extent and some aquifers showed very similar trends. And so instead of having 10, 12 different groundwater flow maps, we consolidated them together to identify these trends. And so next to a specific aquifer, there's a list of, well, if you wanted to know about groundwater flow for that aquifer, you would go to figure 7, versus in this kind of lower system of aquifers, you would go to figure 8. And so that's what we're looking at right here, is that upper system. It was the first 4 buried aquifer units. All of the little gray the points and symbols are all of the different well points that we use to make this map. Okay, so very sorry about the delay, and for those joined online, the technical difficulty. To reiterate, we're at a point where we're talking about bedrock aquifers and stratigraphy at this point, and the major aquifer systems used across the county are the Upper Tunnel City Wanawak, which is kind of this portion, which there are a couple of aquitard units or protective layers within it. But at the same time, for many years, they would drill across both and actually collect water from both. So they had higher yields and could get more water out of it. This is no longer legal. They can't actually case a well or like put a screen in that crosses aquifer boundaries in case there's some type of contamination. But if there's older wells, which there are, they are grandfathered in. And so we have discussed them kind of together. And then we'll also talk about the Mount Simon aquifer. And some of the St. Lawrence formation is kind of the shallowest protective layer, but it's not very extensive, if I recall. Yes, thank you, Tony. And then the Lone Rock formation in the Tunnel City group and the Eau Claire formation are our major protective layers in the bedrock aquifers. So we also made groundwater flow maps for these 2 major bedrock aquifers to look at how water is moving in these bedrock aquifers. This is the Upper Tunnel City group and the Wanawak group. Again, all of the different little symbols are different locations where there's wells in the county. As you can see down here in the southeastern part of the county, there is quite a few wells that are in this unit. Overall, what we're seeing for flow is we still do see a bit of flow towards the Rum River and a split towards the St. Croix.
How, based on the information you have, how do you determine the flow at this depth?
So we look at the elevation of water in each of the wells, and water moves from high elevations to lower elevations. And so the color of this map is created by essentially making points at every single one of these wells with the elevation of water. And then we contour the map, and flow is kind of perpendicular to these lines. And so the arrows are showing the direction of flow. Sorry if I did not clarify that earlier. All buried aquifers are under pressure. There's a lot of sediment and water above them, and they are blocked by a protective layer, and so there's just like a lot of pressure on them. So if you put a well in them, water levels are often above the top, that protective layer. They go up, and so we can contour what the elevation in the wells are to get an idea of what direction water is flowing. Thank you for asking. We then also have a flow map of the Mount Simon Hinkley aquifer. This is the one that's extensive across much of the county. You can see all of the little symbols. Again, not as many in the southeast because that is where that other aquifer exists. So a lot of people are pulling water from that shallower aquifer. And what we're seeing here is, yes, there's not a ton of data in the southern portion here, but we see more of a regional flow. Instead of flow going directly towards the Rum River, we are actually just getting more of a just regional trend of flow from northwest to southeast. Once we get down here, because it's a little more separated from what's happening at the surface and what's moving in the shallow system. We then can move into our next major section of our report, which is talking about water chemistry. This is pages 18 to 29 in your report, and it is also your plate 7, the first of the big paper maps. So for our work, what we do for sampling is, so we typically go out in a county and we sample 90 different wells across a county, and we try to get all of the different depths. We try to represent every single aquifer that has at least 1% of the wells in the county. And we're sampling to see what is the water chemistry. Are we seeing impacts from human uses at the surface? And we do some age dating on it. And we also collect 10 lake samples as well. And we'll talk about what we kind of use those samples for. So all of our, in the end though, we also add in, we look for historic data. We collect some data from the Department of Health. If there's county data available, we really try to hunt down as much data as we can to include in our reports. And in total, in the end, we had 121 groundwater chemistry samples and 11 surface water samples that we used to make our maps or to aid in our mapping. The groundwater samples, we sample for general chemistry. These are major cations, anions, trace elements. Kind of some of the big ones are, we look at nitrate, chloride, arsenic, manganese. These are things that may have human implications, but they may also tell us whether or not, if there's some land use at the surface, if it's showing some impact on the groundwater. And for the ones that we ourselves sampled, we provided all of our results to the homeowners. It's a voluntary program. We send out letters and get responses and sample and send them reports of their data. We also sample for something called stable isotopes, and this is also where the lake samples and surface water samples come in. So hydrogen and oxygen make up water. We look at the isotopes of those. It's a fancy way of saying within hydrogen and oxygen, there's heavy parts and light parts. And if it sits in a lake or a wetland for a while, it evaporates. And so it becomes concentrated in heavier things. And so by looking at the ratios of those isotopes, we can tell whether the water fell as rain or snow and directly went into the surface or into the ground and into the aquifer system, or if it sat in a lake or a wetland for a while, which is indicating that that surface water feature might be recharging water into the groundwater system. And then one really crucial thing that we look at is called resonance time. And we're trying to get an idea of how long it's been since that water fell at the surface and to the source that we're pulling it from. So is it taking, 90 years or less, or 80 years or less for water to be rain and then be pulled out of your well? Or is it taking, say, thousands of years for that water to get there? And we use what's called tritium. And tritium, if they did nuclear bomb testing in the 50s and in very, very, very small components that are not harmful for humans, any precipitation, be it rain or snow that's fallen since the 50s, has a minute amount of tritium in it. And so if we find that in groundwater, it means that that water has entered the groundwater system in the last 70 years. Whereas for longer time scales, we use what's called carbon-14. And so with tritium, if we don't find it, we know it's older than, say, 70 years. We go back to a subset of our sites that didn't have the tritium, and we identify, well, are we talking about a couple hundred years? Are we talking about a couple thousand years? And this can be used and here the results for Isanti County is we found between 550 up to 5,500 years is the kind of longer ages. And so to start out, we have a plot, figure 11 on page 20, talking about those stable isotopes. Like I said, we plot hydrogen versus oxygen to try to see, is there evidence that surface water features are recharging groundwater resources? So on here, this black line, this global meteoric line, that is where you would expect like rainfall or snow, like that's regular precipitation directly infiltrating. Whereas all of our lake samples that we collected we use them to make this lower red line, the evaporation line, which tells us that there is a signature saying, yes, these sat at the surface for a little bit before they got into the groundwater system. So all of these gray diamonds on the bottom left are groundwater samples we collected that seem to be following primarily that global meteoric water line, implying that they were recharged from directly at the surface, versus if you follow the red line, any of the red diamonds, which there are 7 of them along that line, have an indication that they are interacting in some way with the surface water body. And so we also have a map available of the locations that we found that. We definitely cannot say that this is the only place that these are existing across the county. We have a subset of data available to us, but we did find indications in multiple portions of the county that surface water bodies are recharging into the groundwater. Yes. Yes. Yep. And I would also like to point out one very small nuance is these points, they don't have to be that the lake that exists there right now recharged it. These are irregardless of time. And so you could have a glacial lake that existed there many years ago, that water is actually from that very old lake. And so we do have some counties where we have encountered data that indicates a lake signature, but its age is greater than that 70 or 100 years. And so it is kind of a separate thing. And so I just like to make it clear that it's not an indication of time interaction. We have figure 13 in our report is talking about chloride concentrations across the county. I will note we only have figures and maps for a couple of chemicals in the report, but we have descriptions of multiple other chemicals that may not have seen any type of spatial trend. And so definitely look at the report. For chloride, what you'll see is all of the different points on here, be it the little dot or the bigger symbols, are all points where we have chloride data. And there's the size of the point is telling you how much chloride there was in the sample. And then there's a circle or a triangle that indicates circles are buried sand aquifers and triangles are showing us bedrock aquifers. And then if it is an orangish yellow color, that source of chloride is what we call anthropogenic, which what that means is we think that the source of that chloride is human impacts at the surface. So we've identified these as sites where something at the surface is probably the source of that chloride, versus you have one sample over here in the bedrock by Green Lake that is naturally elevated. And what that is it's quite deep. It's from the Mount Simon. And we suspect there might actually be, in very deep units, you can sometimes have what are called brines. And in very, very old units, you can have very salt-rich water pockets. Did you have
I think the internet connection was dropped for us. I don't know if I've lost the child. Yeah.
I'm gonna just check. I think I'm good because I signed into my phone as the internet. Sorry about that. And so across the county here, there was a total of 29 of, I believe, roughly 109 sites that we did identify chloride being elevated or greater than 5, and 28 of those were likely from human impact. So it's roughly 26% of our samples had chloride, but none of them are above any type of health risk standard. It's not harmful for that chloride to be in there. It's just interesting to know and note that there is an interaction taking place. Yes.
You think that's coming from their salting of the roads, or
That is probably a large one. The biggest concentration you see that where we encountered it is over here by Cambridge and down by Isanti, which are by major roadways. But other possible sources like water softener salts, especially, you know, if you have a water softener at your house and you have a septic field, some of that softened water might be going out there. That could be another source of salt, as well as there are some fertilizers, things like that have some salts in them. Figure 14, we have a map showing arsenic concentrations. So in Minnesota, a lot of it is not uncommon in our geologic layers for there to be a source of arsenic that gets into our groundwater. At the Department of Health, the health risk standard for arsenic is 10, but they have a goal of having none in your groundwater. And so across your county, on this graph, we show a cut of 2, which is a relatively low amount. And so on this map, we can see anything that is between 2 and 10 is kind of this yellow color. And anything that's greater than 10 or that health risk standard is a bright orange color, which there were some sites where arsenic was above the health standard. This is something that, while it doesn't tell us much about how the surface and the groundwater are interacting, it is a possible health concern. And so we definitely encourage people to have their well tested if they have a private well for arsenic, since it is present in your county. And then we have those kind of residence time indicators we were talking about, or how long it takes from the surface down to these different groundwater resources. And so we call something modern, or if it's something that we know has enough tritium of that tiny isotope in it that we can see it in our groundwater samples, that's modern. So it's gone into the ground since 1953. And then we have down to pre-modern, anything in the blue that is actually water that we didn't see that signature in. And we suspect that water is older than 1953. And then we also have mixed, which is kind of a mixture. And you may see stuff in our report about mostly pre-modern. And it's a weird gray area where how we would classify between mixed and pre-modern exists below the detection limit of the instruments at our lab. And so we very much suspect that it is pre-modern, and we bump them together in most of our report, but we just like to clarify the difference. Of the samples for tritium, 31% was modern, 21% were mixed, which both of those show an indication that since the 1950s, water is reaching that groundwater. And then pre-modern was about half of the samples. And then those C14 ages, we had 16 for your county because we had some historic data for that Mount Simon project that's been mentioned a couple times. And we had ranges between 550 to 5,500 years, with the kind of sand and gravels were between 550 and 900 to 1,000. And below that in the bedrock aquifers, we had a little bit older ranges. The water chemistry plate 7, gives us a broad overview of all of those different chemistry points. It summarizes most of the information I've just talked about in the chemistry section. It has tritium age, it has all of the different aquifers by symbol, as well as it shows labels of all of the different chemistry things. So the orange labels are manganese, which across the county, it was very present. 90% of our samples had elevated manganese, and it was actually above the health standard. So that is another thing that we would recommend you definitely look into if you have a private well. But we don't have a map of it because it was so widespread that there's no real spatial map view story for it. The geologic layers. There's just naturally within the rocks and the sands and gravels, the water leaches it out through time. Yep. And then we have a pollution sensitivity section. We have 2 different primary pollution sensitivity maps. The first one is the near surface map. For these, we are looking at we are modeling how long it takes for water to fall at the surface and reach a depth of 10 feet. So the very shallow portion of the county. The top 3 feet we classify with soil data. And then from 3 to 10 feet, we use the surficial geology map from the MGS, and we use the textures of those two things to actually calculate a transmission rate, or how long it would take to transport to that depth of 10 feet. We say things are high sensitivity on this map if it's taking hours up to a week, all the way down to like a very low rating is like months to a year. So these are relatively short time scales. And generally coarse grain material, so sand and gravel, it moves things quicker, so it has a higher transmission rate versus fine grain materials are lower. This is our map here in Isanti County. It's figure 17. Over much of the county, you'll see it's bright red. That's where we have those coarse grain, really sandy materials at the surface. Versus where we have different till units at the surface, it's a little bit more protected. There's also a crosshatch pattern on here that's indicating the areas where there may be peat at the surface. We don't know the exact thickness of the peat. We display it as an overlay to just indicate that it may adapt, impact these sensitivities because it could adjust how groundwater is flowing. We then have what are called buried sensitivity maps, which we make for every single one of those buried sand and gravel aquifers, or most of them. And then we also have one that goes all the way down to the bedrock surface. So we're looking at that whole thickness of unconsolidated material. And we look at those protective layers, those tills, and we add up the thickness above to see how protected it is. And we say it has very high sensitivity if there's less than 10 feet of protective till above it. All the way down to very low sensitivity is where there's greater than 40 feet of protective material above it. I do point out the timescales on this are much longer than what we talked about on the near surface, that we were talking up to a year, whereas the time ranges for these, we're looking up to decades and centuries because we're further into the subsurface. So how this works, if you looked at location A here, if you were in buried sand 1, there's only 5 feet of protective material at this point. It's very high sensitivity, versus if you move into another buried sand, you add another 7 feet of protective material, or maybe in high sensitivity for that aquifer at this point. And I also like to point out at B and C here, you can be in the same sand unit, but at one point there can be 23 feet of protective material, but at another it could be 41 feet of protective material, which is very different classification ratings. And so that's why in a single sand body, you may see drastically different, because we are only looking at a vertical model in our report. To discuss the fact that, say, in that specific sand body, why we might have a higher sensitivity sample in it, because over here it's unprotected, and say water flows that way, not vertically. We do put what are called recharge indicators on our maps to explain why that chemistry might be there, even though the sensitivity may indicate very low. So lateral is when up gradient, it looks like there's a less protected area and it's bringing water that's younger than expected. We can have a P for if there's an indication of a high volume pumping pulling water. Near Cambridge, there's a little bit of an indication that like lots of pumping is pulling more recent water a little bit deeper down into the subsurface. We have a D for discharge, and this is kind of the opposite. We're seeing less sensitive sample than we would expect. And that could be, this is a very big regional discharge point, and deeper, older water is actually upwelling and discharging to a point. And then there are cases where we just don't know. There could be a well construction issue where water is kind of seeping down the side of the casing. And in some cases, geology is not uniform. We can only do what we can. And so this is an example of a shallowed buried sand pollution sensitivity map. This is the first buried sand aquifer. You can see a lot of reds and oranges and yellows. Those are all indications that there's not a lot of protective material over this sand body. There's symbols indicating the tritium age, as well as if we had information of elevated chloride or nitrate or arsenic, that is also indicated on these maps. Versus this is what it looks like when you get down to our bedrock surface. So at the very bottom, below all of that quaternary or that sand and gravel, we add up all of the different tills, and at the bedrock surface, we still have actually quite a few little pockets where there's not a lot of protective material within the sand and gravel. And so we do still have some sensitivity. On this map specifically, the symbology is actually showing the fact that all of the different bedrock data is shown on this sensitivity map. And so in some cases, you can have really high sensitivity next to some very low, modern data versus pre-modern data. And that's just a function of, this is the whole series of those bedrock aquifers shown on the same figure. And then we've included in this report pollution sensitivity of all the buried aquifers. When we worked with some of the previous counties, they found it beneficial to look across their entire county and see, well, if I hit my first buried aquifer, is it high sensitivity or low sensitivity? And so we consolidated all of our different pollution sensitivity maps together, and you can kind of see all of the different areas where the first aquifer you hit has high sensitivity. We then have cross sections, which is the second big plate that you have, and that's on page 46 to 47 of the report. We have published 7 different cross sections for our report, and this is what the final report looks like if you open it up. There is a map that shows all of the lines in black are the ones that we published for our report, and the orange ones are the ones that they published for the part A, if you wanted to try to compare the geology and hydrogeology. We'll do just a little quick look at one of these cross sections to talk about some of the stuff on it. So if you look here, this is the map. We have a C to a C with a dash, or C prime. And then on our cross section, we have a C and a C prime. And so this is if you dug a trench east-west across the county, the subsurface, and we've color coded it based on hydrologic or groundwater information. So any of the aquitards, like we said earlier on those stratigraphic columns, any of the gray shades are those kind of protective layers on the county. If you got into the bedrock, in some of the cross sections, you'll actually see kind of this like tealish color. That's when you have an aquitard or a protective layer within the bedrock all across the bottom here. We then have the aquifers on our cross section. Every single one of those different patterns that we talked about on the stratigraphic column exist on the cross sections, and they are color coded based on their tritium age or interpreted tritium age. You'll also see we have all of those sticks like they did in the part A. Those are all of the different wells. And if you see the kind of box on the bottom, if it's a gray, it means we don't have chemistry information. But if it's colored, it is actually colored based on the tritium results that we got for that well. And then we also have symbols to show what is the chloride at that well, what is the arsenic at that well, as long as they're above a certain threshold. And then we have the recharge indicators. If it's in an area that we see a higher sensitivity than or a higher tritium value than we think, based on our pollution sensitivity mapping. You'll also see these dashed lines and arrows. We also kind of make, we display the direction of flow across the cross sections as well. So we look at the water level in all of the wells, and we actually plot out how water is flowing across the cross sections. All right. And within the report on those 2 pages, there are like narrative descriptions to go along with all of these cross sections. The last section of our report is called Aquifer Characteristics and Groundwater Use. In this section, we have a bunch of different small topics that largely are presenting data that may already have been published or things that are good to know about. So aquifer characteristics, this is table 2 on page 48, showing specific capacity and transmissivity. So we look at the county well index as well as we look at historic records of what are called aquifer tests that people have done to understand the different properties of aquifers and how water moves through them. And we compile that information and provide it. So if somebody, say, was doing a groundwater model, they might have a place to start with values or information about whether tests are available in the county. We also look at the DNR has monitoring wells across Isanti County and across the entire state, and they are tracking long-term how that elevation is changing in aquifers. And so figure 31, it actually combines a couple things together, but at locations 1, 2, and 3 are actually observation wells that the DNR maintains that we have provided long-term records and talked about the trends that we see in those wells and how water is moving at those exact locations. And on this graphic, you can also see a little bit, we talk about groundwater use. The DNR also monitors and does permitting for large users. If you use more than 50,000 gallons a day or 1 million a year, you need to get a permit from the DNR. And so we have actually provided also here, we're talking about what unit being used, and as well as the size of the symbol is how much groundwater use is used at those different locations. And then this is an example of one of those long-term records, a hydrograph. There's 3 different ones discussed in the report. And then the groundwater use, we summarize it in a table by which aquifer type is being used. Primarily, for aquifer type, as Tony brought up, if we look at percentage-wise, the large majority of our water use is from those deeper Mount Simon and multiple unit wells and aquifers, but definitely the bedrock units are largely being used by these larger consumers. And then the main uses across Isanti County that are permitted are a combination of water supply and irrigation. And we have a figure, when our final figure in the report, figure 35, is actually showing where the different types of use are and how much use. And so as Angela pointed out, the green here, darker green is that irrigation wells, but there are also multiple water supply wells as well that are pretty big users. And so kind of in summary, there's coarse grain material at the surface that is most, blanketing like roughly half and makes up 7% of the wells in the county. There's 3 main surface watersheds, that Rum River, Snake River, and the Lower St. Croix River, which that Rum River and Lower St. Croix are showing groundwater flow towards them through most of the aquifer system. As I just stated there, buried sand aquifers are the main groundwater source by number of wells at 67%, followed by bedrock aquifers at 26%. The pollution sensitivity of the near surface materials, the shallow system, is high through most of the southern part of the county, but there are areas of lower sensitivity to the north. There is anthropogenic chloride in about a quarter of the county, and I will also add, not listed up there, that manganese is pretty prevalent across the county, as well as there is a bit of arsenic, which may be of concern for health reasons. And then municipal water supplies is the largest permitted user of groundwater at 55%, followed by groundwater irrigation or agricultural irrigation. Does anybody have any questions? Yes. I do not know. For our specific, there is a way to measure. You can collect samples and measure PFAS chemicals. For our work, so PFAS, it gives the same rough time scale or not far off of it of tritium. And so right now we use tritium to do age dating, but it may be of something of health concern, which for our study wasn't the primary focus. But I do know the Department of Health is gearing up their PFAS sampling protocol to start do more of that.
The Department of Health has sampled, I think, virtually all the community supply wells for PFAS in Minnesota. Public supply wells, not private.
But I'm manager of the Soil and Water Conservation District, and thinking, from a voluntary groundwater protection standpoint, are there any opportunities or things that kind of stand out?
I think a big thing in my mind is encouraging people who own their own wells to sample them. I think that is a very big one. There's an organization in Minnesota called MNWOO. If you have not heard of them, MNWOO. It's like Minnesota Well Owners Organization, I believe is what it's called. They have started putting on a lot of sampling clinics where if people bring in a water sample, they'll do some chemical analysis for you on site, which is a very good resource. But so, in Minnesota for public water supplies, like in Cambridge or Isanti in a city, they have health standards that they have to follow and monitor that water for. But anybody who owns a private well, there's no legislation, there's no requirements for them. And so just encouraging people to get their water tested, especially here in Isanti County. Like I said, manganese, I forgot to mention, beyond the fact that it's, we found it in 90% above the recommended health limit. It was like the limit is 100, and we found ranges from 100 to 1100 for the concentrations. And arsenic as well. We know it can be present in Minnesota, and just encouraging people to get their well sampled.
That we sample free any filtering in the home.
That is a good.
So yeah, this is not necessarily what you're drinking, but it's like free filter, free water softener. So I think information about that as well. There's a lot at the health department on like what filters to be using for what contaminant. So just getting that information out as well. Even if they don't, like based on our map, they could get some idea of what might be in their area and like how like they put their water softener to take out most of that.
Or in a lot of cases,
if they don't want to get it.
A lot of things too for like arsenic and manganese, even just having a tap or an RO faucet on what you cook with and what you drink could be enough, because these are things that it's not like when you shower in it, it's a problem. It's your consumption of it that it's more of a problem.
How often do you suggest them sampling? Once a year, once every 5 years?
I don't want to say, because it's a Department of Health has an entire well department, and they have recommendations.
I can give their recommendations.
Yes, please. Yes.
So Department of Health recommends testing annually for total coliform bacteria, which wasn't mentioned here, and nitrates. And then at least once for arsenic, lead, and manganese. And if you do find arsenic, lead, or manganese, then they would recommend follow-up testing once you've decided how you're going to treat or mitigate that.
This is Brenna Finley, by the way. And
Thank you, Brenna.
could you say just a couple words about
What you're working on?
You and Kate are working on? Because
Yeah.
it's relevant to these questions.
Yeah, definitely. Hi, everyone. My name is Brenna Finley, and this is my coworker, Kate Finke. We're here from the University of Minnesota Extension. we recently received some grant from Minnesota Department of Health to start a private well education program. And so we are currently developing a program. And it will have a few different aspects to it, but one of the things we're working on right now is a free online course called Private Wells 101, and it's really geared for individuals who rely on private wells in Minnesota. And it will go over some of these things like water quality, what to look for based on where you live, and what you might consider for next steps. We are also piloting a new group called Minnesota Well Water Stewards, who will be hopefully a peer-to-peer leader network to have some of this information and be able to go out and talk to their neighbors, table at county fairs and things like that. And then finally, similar to the work Vanessa mentioned that Mingo was doing, in the spring, we're hoping to pilot a few drinking water testing clinics where folks can come and receive a test kit to test their well water for those 5 contaminants that the Minnesota Department of Health recommends testing for, and have a follow-up educational workshop similar to what's going on here today. If anybody has any questions or wants to chat later, though, we'll be here.
Any more questions?
I was just gonna ask if soil and water, like in the area that you're working, like here.
Yes, great question. We are working to connect with soil and water conservation districts in the areas we're working. We're piloting the program in 6 counties in central Minnesota, north of here, and also in northwestern Minnesota. And in addition to soil and water, we're also trying to partner with local public health, and then some extension members. Yeah.
All right. So for the rest of the workshop today, we are a smidge behind schedule. What we do have for you is actually we put together just some exercises to try to get you some hands-on experience with the reports. But the first thing I wanted to kind of present to you guys, which as we do this, grab a little coffee if you need to, or snacks. I realize we've been going for quite a bit here. Okay, so this will be a little tricky. So we've heard county well index a few different times. What it is since the 1970s, there's been a legislative requirement that if a new well gets put in, they actually have to submit a record for that well, so we know where it's located and some additional information about that well. In the last handful of years, they've developed a good online interface called the Minnesota Well Index, and that's the actual online interface that you can interact with. If you just go to Google and type in Minnesota Well Index, sorry, I'm typing on a different screen here. First thing that comes up is the Minnesota Well Index. If you click into this website, hopefully it works. What you can do is it will automatically bring up kind of this map view version. And what you can do on this website is, does anybody have an address? They are. And then, does that look right? That one? Yep. Okay, I can't see it. I'm blind. You can zoom in to an address. And what you can find on the website is anywhere current dots on here, that is a registered well in Minnesota. And you can click on this well. Hopefully, I will get there. You have to get right in the center of it. It's even harder when it's on a different screen. So not. it's also connected to my phone for internet, which may be really slow, so I'll let it sit a sec.
I think it's to go for Google page for the people online. Like 30 minutes to well next first.
Oh, all right. Hey. Oh, there we go. All right. So on this map, it shows you the number, this unique ID number. That's the number in the database associated with that well. It'll have the name that was submitted with drill record. So, you know, this is probably the person who owned the property when the well was drilled. It has the elevation of the well, what aquifer, QBAA would be like a that's the quaternary buried aquifer. So that's one of those buried sand aquifers, and it tells you how deep that well is, 110 feet. And then you can click see more information, and within this, it will pull up, like shown by Angela and Tony, there's a whole well record that shows. So this is the main page. There's things like the well log record, the scanned record this is the actual physical copy that was submitted and scanned in. And you can into one of these, and it will give you information about, once it goes up here, kind of look at it. But what this can be useful is if you bought a new property and you need to put in a well, and you want to have an idea of how deep do I need to put my well, you could go to this website and see what people here have for their water resource. If you property that already has a well, don't know anything about the well, you can go here and look at information provided on this website. And so this is what it looks like. It tells you how deep the well is. It tells you how deep the well is. It tells you if there's a stream, like what depth it's actually pulling water out of. And it also gives you an idea of their sand, and then there's clay, and then there's the layer that they're pulling water out of, which this is the information that they use at the Geologic Survey to make all of these geologic maps. These are the types of records. But I just like to provide this for people so that they have an idea of this resource that they can use. You can also reports and kind of back and forth of, well, is this area really susceptible to contamination? Are there water chemistry samples nearby? Things along those lines. All right, so this last portion of the day is kind of meant to be a hands-on portion where you're actually getting your hands on the report and doing a hypothetical situation where you might apply our product. And so, for example, we'll do a hypothetical situation, definitely not a real situation, but there's been a tanker truck spill. So accidentally, unknown liquids were released. Emergency responders are asking you about potential groundwater impacts. What's going to happen? Are there things we have to be concerned about in an area? And so the location is along Highway 95, north of Green Lake. And so just to give you an idea of where we're looking, if you're like looking at your report or your map, you could start your assessment, right here north of Green Lake is where this has happened. And we want to kind of look at our report and see what information we might find out about that section of the county. And so here, what can we quickly gather from the groundwater atlas? So my first kind of question is, that I would think to start with is, if we're talking about groundwater or the water resources, is, are there any surface water features that could be impacted by the spill in this area? And so where might you look in our report to identify if there's any type of surface water feature? Anybody? Yeah. So many of our maps will have surface water features listed on them. In this case, that first map where I had circled the location, this is figure 1. in the report on page 4. This is just a location map showing you all of the a lot of the different roads and surface water bodies and watersheds here in Isanti County. And so off the bat, are there any surface water bodies in the bright red oval that might be impacted by a spill?
Yes.
Yes. Okay. So what do we have in our little circle? We have Green Lake. Yes. We also have like the nice little stream. Huh?
County did 16.
I just had miscellaneous stream listed. I did not look up the exact ditch number. So a stream throws, County Ditch 16 flows through the highway in this area with Green Lake directly south of it. Next question I might pose is, what is the surficial geology near the spill? Will the chemical move through it readily? So what is the type of unit? In the paper copy of the report, many of you may be seeing there's kind of like an acetate overlay. The purpose of that, the little clear plastic, is if you wanted to look at a specific area, you could circle it on that, and it goes over every single one of the maps in the report, so you could consistently see the same exact area. Just to let you know. Does anybody have thoughts on what figure we might use to look at the surficial geology near the spill?
3.
Yeah. Figure 3 on page 8. That is our generalized surficial geology map. And is there, what type of unit is there? So we got lots of yellows, right, in the oval. And the yellows mean it's sandy. So it's very sandy. So is some unknown contaminant going to readily flow through that? Yeah. All right. Something. So there's surficial sand under this area between 0 and 70 feet. So it's the sand in this area. There's also some connection between surficial and buried aquifer units as well that might exist. And so that might be, depending on where exactly it's spilled, something you want to be aware of. What direction is the groundwater at the water table moving in this area? So if this spill happened, we might want to know where it's going to move, right? Once it gets into the subsurface. Which figure would you use for that?
Figure 5.
Figure 5, correct. And what is figure 5 showing us? Yep, it's going right down to Green Lake. And so, yes, exactly. So the site is within the Rum River watershed, and flow directions are south and east towards Green Lake and to the nearby stream that's crossing the road there. We can clearly see that there's some water feeding into that from the water table as well. Is there any indication of surface water recharging the groundwater in this area? So do we have an indication that there's an interaction between, say, a lake and the groundwater in this area? Does anybody know where we might look in the report for this? Sounds a little tougher. Yes. Well, it's figure 12 is the map, but figure 11, that's that stable isotope information we talked about, identifying where we have well water or groundwater samples that indicated that it's interacting with a lake. And so within our kind of circle here, in Spectacle Lake and Green Lake, we collected surface water samples, and right outside of Spectacle Lake, one of our well samples did indicate that it's being recharged by the lake. And so there may be some interaction between those surface water bodies and the groundwater system in this area. What is the near surface pollution sensitivity in this area? Which figure might we look at for this?
Figure 17.
Yep. So figure 17 is our near surface pollution sensitivity map, and what are we seeing here? It is high. Yep. High surface, near surface pollution sensitivity, and there is a little bit of peat along some of the streams as well. What about pollution sensitivity of buried aquifers in this area? You'll see that there may be numerous buried aquifers, but starting at a shallower aquifer where it would first encounter is probably a good place to start. Anybody know which figure that might be to look at? So this one, I used figure 21. Figure 21 is the pollution sensitivity of the buried CSA aquifer. So this is the very first buried aquifer in the subsurface. And is this aquifer present? What is the pollution sensitivity in this area? High. Yep. So again, we have some high sensitivity areas. We can also see on that pollution sensitivity map, we also have listed, we have shown those locations of all of our cross sections across the county. And while it's not directly under where the spill took place, we see that D to D prime is right to the south of where the spill took place. So we could go to the cross section and we could take a look at what's going on in the cross section underground here. And so what we can see here is, you know, we have sand and gravel anywhere between 100, 150 to 200 feet thick. And we can see that there's surficial sand that exists over a lot of this area, except maybe in this case, we're south and we're directly under Green Lake. So at the base of Green Lake, there's a little bit more of a protective layer just from sediment depositing out of the lake. But otherwise, we have a lot of surficial sand in the area. And then we can also see that there's buried aquifers in the area. So we have the CSA aquifer in a few different places. We have the CSR aquifer, CSC. And so there are some that are susceptible to pollution of those aquifers. And then the last thing that you could maybe look at, which I mean, there's numerous other things you can check, is what groundwater use is in the area. So are there people using water in this area that may be concerned about this spill? This is kind of a two-part question. Anybody have thoughts on where we might look for groundwater use? Yep, groundwater appropriation. So you can look towards the, huh? Yep.
What's the recreation?
Oh, recreation. Yeah. Yeah. Sorry. No, it's fine. So one thing, so I had put the water use map. So you can, and this is like our permitted data. And you can see that there are some agricultural wells and special categories wells. So there are a few bigger users of water in this area that might be pumping water at a higher volume. But so there's irrigation wells in the area, but there's also likely domestic supplies. Those are private wells that people own. And so one way you might take a look at that is if you look back at the cross section, if you look, all of these little lines and boxes are wells. So there's numerous private wells that might be accessing water in this area, as well as some of them are actually in some of these shallower units. And so, and you could also go to that Minnesota Well Index. You could search the rough address or zoom in to this area and see what well users are around and who might be, you know, a little concerned about that. Does anybody have any questions? Yeah.
How much those information used in real life by emergency responders?
I don't know the exact application rate of our materials. I have done presentations and coordinated with many local units of government about projects that they're working on. We do presentations like this. I've also done presentations too. Technically, it was the Department of the Defense, but it was emergency responders. I've gone to presentations and presented them with this information and our different resources. But being that I do not work on that level, I cannot know exactly how much they are applying it. Yes.
The city never instantly emergency responders, firemen. Allows them to deal with spills, whether it's say like a derailment on train lines or highways. That would be great. No, but they can something that you put their fingers on right away.
I will note our product, while not currently available in the state, we are working on making. So the part A has what are called story maps on their website, and it walks through their product and you can interact with it and you can zoom into areas online with their digital files. At the DNR, we do not have that up and running yet, but we are currently working on a similar thing so that our individual county data, you could, if you don't have access to a GIS software or know how to use GIS software or what it is, like you could just go to our website and click on and off layers and zoom into an area. And we are currently working on getting that interface up and running. And we do plan for most of our historic counties to try to get them up and have a website available to them. It's a lot of data on a larger scale than an individual county. But what I've given to first responders and emergency responders before is we have those other databases I mentioned before of springs and dye tracing and things like that. Especially the dye tracing database, it actually shows the springs and the karst features on it. And it shows the locations across the entire state, and it has some layers available to turn on and off. And so I point them to that, and you can zoom in and you can see different things that are available at this time. And so not ready yet, but we are definitely trying to have exactly that you could go to our website and you could just look in your precise area instead of having to go to a PDF or have your own system. Yeah. Any other questions?
How is it that rock?
For those online, we just had a question that has to do with the deep bedrock valley across Isanti County and how we know how deep the bedrock is in that area.
Right. There will be the rare well that does go that deep. And if one well goes that deep, because this is a former drainage, we know it has to kind of stay that deep going in some direction, right? to maybe one other well we'll find several miles away. But what we also do is we use geophysics to determine depth of bedrock. I'm not a geophysicist. I'd make a lot more money if I was. And they use a technique called, where we work, called passive seismic. You've heard of seismic exploration. Passive seismic just picks up ambient seismic shaking, trucks going down the road and that. And the signals from that bouncing off the bedrock can provide an estimate of depth of bedrock. And it's just basically a little black box. It's actually yellow, but we have field techs who just set them down with a laptop, collect seismic signals for 30 minutes, and we process the data. Yeah, then 15% or so error of depth of bedrock.
York County, we've done active. And so people would actually go out with a 7,000-pound trailer with a big piece of concrete, and you put out different acoustic nodes, and you hit the ground and you measure how the sound waves come back to try to model that depth of bedrock as well. Yeah. Anything else? Well, thank you again, everyone, for being here today. And again, thank you, Samra, for helping.
Do you get grades on the exercise to people?
No, you do not grade on exercise.
Yeah.
We're just happy. And if anybody has any follow-up questions, anything at all, please reach out to any of us. If you'd like any type of follow-up, you keep up involved.
Survey that's dropped on your way. That's your email address. Or there's a little QR code to apply later.
Yep. And for those online, it has been dropped in the chat. If you could please fill out the survey, that would be fantastic.